In this video, we're going to talk about different sets of numbers, and each of these sets has a particular name, vocabulary word that you're going to want to memorize. So you might want to get a piece of paper and pencil to write these words down. If you're like me, it helps to write them down as far as remembering them. The first set of numbers we're going to talk about is called the natural numbers, or also they're called the counting numbers because they're the first numbers that you use when you learn how to count. They start with the number 1. That's the smallest natural number. And they go 1, 2, 3, 4, 5, 6, 7, like counting numbers. Now notice at the end here we've got a dot, dot, dot. What that means is that this set goes on forever. So if we kept counting, eventually we'd get to 1 million. So therefore 1 million is a natural number. 1,000,001 is a natural number, and so on and so on and so on. The next set of numbers is called the whole numbers. Now the whole numbers are pretty much exactly like the natural numbers with one exception, and that is the number 0. The whole numbers start at the number 0, and then they just contain all the natural numbers from there. So the whole numbers and the natural numbers are pretty much exactly the same except for the number 0. The next set of numbers is called the integers. Notice with the integers what we've added are the negative numbers. We've got all the whole natural numbers that we had before, 1, 2, 3, 4, 5, etc. We've also got 0 in there like the whole numbers. But now we've added -1, -2, -3, -4, and we have dot, dot, dot because it continues that way forever as well. -5, -6, -7. So -843 is an integer. Now positive 843 is also an integer. Positive 843 is a whole number, and positive 843 is a natural number. So it's possible for one number to belong to many different sets. And we're going to see how all these sets of numbers relate to each other in a little bit. One place that you would see integers is on a number line. Many of you have seen a number line like this before, where their numbers are marked 1, 2, 3, 4, 5 to positive infinity. This 8 on its side means infinity. And then to the left, we have the negative numbers, -1, -2, -3, -4, -5, forever like that. The integers do not include any of the numbers between 1 and 2, or between 3 and 4, or between 2 and 3. You'll notice that so far we've got positive numbers, we've got negative numbers, but we don't have fractions and we don't have decimals yet, and those are coming up. Before we get to those, let's look at some places where we would definitely need negative numbers in our lives. Temperature is one place here. Unfortunately, I'm not a big fan of negative temperatures, but we need negative numbers to express negative temperatures. I found this little example from an article. The Falcons' longest run against the Steelers was just 7 yards, and Turner got just 19 carries. 4 of his carries went for negative yardage, and he has not received more than 20 carries since Week 5 in 2009. What does negative yardage mean in football? Well, those of you that are familiar with football know what the line of scrimmage is. That's where the ball is placed when it's hiked. If the guy gets tackled behind the line of scrimmage, it's considered negative yardage or a loss of yards. And in totaling his total yardage for the day, they would count that as a negative number if he got tackled behind the line of scrimmage. This is an inappropriate use of negative numbers. I found this picture is kind of funny. I think somebody accidentally punched in -1 as a baseball game here. -1 balls and 5 strikes. I don't think so. Some places you wouldn't use negative numbers. If we're talking balls and strikes, we would want whole numbers for that. Don't need the integers to talk about balls and strikes. Earlier I mentioned that we didn't have fractions and decimals. So here comes the rational numbers. This gives us our fractions and our decimals. We can't list out all the rational numbers like we did with the other sets of numbers, so we have to describe them. And they're described as, a rational number is any number that can be written as a fraction of 2 integers. So you got to remember what your integers are. Remember the integers was -4, well it was dot, 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 -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, dot, dot, dot. Those were our integers. I've thrown in some other integers here that are not on the list. -6, -10, -240. When I say not on the list, I mean that they're sort of in the dot, dot, dot part. I didn't write them out that far, but they certainly are integers. So all these numbers here are integers. To make a rational number, we're going to make a fraction of these 2 integers. So we're going to take one of these integers and put it in the numerator. Let's pick 2. Then we're going to take another one of these integers and we're going to put it in the denominator. Say 3. By doing that, we've created a new number. That number here is 2/3. So 2/3 is a rational number. This is how we're going to create all of our fractions, by taking two integers and making a fraction out of them. One on the top, one on the bottom. Now if you remember, 2/3 as a fraction can also be expressed as a decimal. The decimal for 2/3 is 0.6 repeating. So 0.6 repeating is a rational number because it can be expressed as a fraction. It doesn't have to be written as a fraction to be rational. It just has to be equal to some fraction. So you got to remember that your decimals, many of your decimals, can be written as fractions, almost all of them. As a matter of fact, if that decimal repeats like this, 0.6 repeating, 0.6 ... that bar right there means that this bar right there means that 6 goes on forever. So this is the same as 0. I can't write very well with this. 6, 6, 6, 6. That's terrible. ... forever. You get the idea. Let's try another one. Let's make another rational number. I'm going to pick a negative number for the numerator and 5 for the denominator. -1/5. That's the same as -1/5. And the decimal for that is 0.2. So here's another example of a rational number. With these two examples, we see the two different kind of decimals we can have to make a rational number. We can either have a decimal that stops, like 0.2, and it's done, or a decimal that repeats, 0.6666666. If the decimal stops or repeats, then you're going to be able to write it as a fraction of two integers, and therefore it will be rational. Let's look at another example. What if the top number is bigger than the bottom number, 40/3? Well, we know that is an improper fraction. Improper fractions can be written as mixed numbers. So those mixed numbers are also rational. We could also write the decimal form of that mixed number, which is 13.3 bar. All these different ways to write 40/3 are all rational numbers because they are equivalent to 40/3, which is a fraction of two integers. Let's look at another example, -10/4. This fraction can be reduced to -5/2. So therefore it is a rational number. -2.5 is the mixed number for that improper fraction, and as a decimal, -2.5. So all these four different ways are just ways to express the same amount, which is an amount that can be written as a fraction of two integers, -10/4 or -5/2. Therefore, all these are rational numbers. Let's do one last example, 826/1. What's 826 divided by 1? Hopefully you said 826. Now if you remember, 826 was a natural number and also a whole number and also an integer. So all those natural numbers, whole numbers, and integers, you could write them as that number over 1, and therefore they are all rational. And we're going to see how they all relate to each other coming up. Here's some examples of where you might see rational numbers in your real life. This is the stock market. Even though this is expressed as a decimal, all these are expressed as decimals, 30.96. That's the same as 30 and 96/100ths. So therefore it can be written as a fraction, and therefore it is a rational number. You've got positive rational numbers and negative rational numbers. This day the NASDAQ was down. That's why you usually see it in red. Rational numbers. Other places you see rational numbers. Tape measures have all these fractions. Those are rational numbers, fractions. We've got measuring liquids, weight, measuring weight. Things are not always exactly a pound. You're going to have fractions or decimals in there. We need those rational numbers. And of course, money. 25 cents is 0.25. That's a rational number. Okay, we're going to digress here for a minute and talk about square roots in order to introduce the idea of numbers that are not rational. If you haven't seen a square root before, let's go ahead and look at this. You've got square root of 25. That means what times itself is 25? What times itself is 25? 5 times itself is 25. So the square root of 25 is 5. The square root of 9 is 3, because 3 times 3 is 9. The square root of 49 is 7, because 7 times 7 is 49. what's the square root of 11? What times itself would be 11? 3 times 3 is 9. 4 times 4 is 16. It's got to be somewhere between 3 and 4. It's going to turn out that it is an irrational number. Here's the square root of 11. It's going to turn out to be 3.316624, on and on and on forever. It's not a nice number. The decimal does not repeat and it does not end. Those are called irrational numbers. If you look up irrational number, it's going to say that it's a number that's not rational. Well, that seems obvious, right? Let's think about that a little bit further. Remember, rational numbers had decimals that ended or repeated. So an irrational number is going to be a decimal that never ends and never repeats. These are all examples, common examples. Any square root that's not nice, all these guys right here, any square roots that are not nice are going to be irrational numbers. You'd think you wouldn't see irrational numbers out there in nature, but it turns out if you have a square that's 1 foot on each side, this diagonal length across here is the square root of 2 feet. Even a simple shape like a square has got an irrational number for the length of its diagonal. Another place where you see irrational number is pi. I know you guys have heard of pi before. Pi is circumference divided by diameter. So if you have the diameter, the distance across a circle, how many times will that diameter go around your circle? It'll go around once, twice, 3 times, and a little bit more. As a matter of fact, it'll go around 3.1415926 times. Irrational number goes on forever, never repeats, and never stops. So here's how all these things relate to each other. We've got our natural numbers, our whole numbers, our integers, rationals, and our irrationals. All these numbers together make up what's called the real numbers. Notice how I've got these piled on top of each other in what's called a hierarchy. Every natural number is a whole number. That's why it's underneath the whole numbers. And every whole number is in the integers. And every integer is a rational number. So each number belongs to every set above it. Another way to look at it would be in this sort of a circle diagram. All the natural numbers live in here. And they live inside the whole number, so every natural number is a whole number. And every whole number is an integer, and every integer is rational, and every rational number is real. And then over here, we've got this other set of real numbers, which is your irrational numbers. So they all relate to each other. Let's look at a couple different examples of problems that you might see. To which set or sets does the given number belong? So let's say we have -6, and here's the question. Is it a natural, whole, integer, rational, irrational, or real number? Which one of those does it belong? Well, let's find -6. It isn't natural, that's for sure. It's not that. It's not a whole number because there's no negatives there. It is definitely an integer because it's going to be in this set. Now, since it's an integer, it's also rational and it's also real because it belongs to every set above it. Let's look at another example. 3 5/8. What do you think? Where would that go? Well, there's no fractions in the natural numbers. There's no fractions in the whole numbers. There's no fractions in the integers. Here we go. Rational numbers. There it is. It is a rational number because it can be written as 27/8, which is the fraction of 2 integers. And since it's rational, it's also real. Any of these numbers you work with are going to be real. There's a whole nother set of numbers that are not real, but we're not going to talk about that, and you might run into that later on in your math career, but don't worry about it now. Couple more examples. Square root of 7. You remember square roots? Where do they go? That's right. They're irrational. They have decimals that never repeat and never end. Irrational numbers are also real. They belong to the real numbers. So square root of 7 would be irrational and real. 6.875. Well, 0.875 is the same as 875/1000. Notice this decimal terminates, it finishes, it stops. So therefore it is a rational number. And since it's rational, it's also real. Last one, 87. Well, 87 would definitely be in this list right here of the natural numbers. If we started counting 4, 5, 6, 7, 8, 9, we'd eventually get to 87. Now, since it's natural, it's going to belong to everything above it. It's going to be a whole number, an integer, a rational number, and a real number. So it's possible for one number to belong to multiple sets of numbers. Well, I hope this gives you a good start on different sets of numbers, and be sure to memorize those definitions.